Hello everyone. In this video we will discuss about what is Bayesian statistics and also one of the machine learning algorithm called as naive Bayes, which is used for classification. So Bayesian statistics, it's a branch of statistics that updates beliefs using evidence. So the basic idea is based upon the information what we have, we postulate something as initial belief or the prior, and we update these belief based upon the new evidence which we obtain through the new data. And this updation happens through a famous probability theorem called as Bayes theorem. And Bayes theorem tells us how to revise our beliefs about an event after observing new information. So let us see mathematically how this happens. So where P of A is the prior and P of B is the evidence, which is the new data which we got at this instant. And for the given prior, what is the probability of for the new data which we got, which is called as likelihood. And for the given new data, what would be the how would the belief about the A gets updated is notated as posterior. So we would like to find this posterior based upon the prior information and about the evidence and also the likelihood function. And this is what Bayes theorem gives us all about. So this is the expression for it. And let us now see how this simple Bayes theorem will be applied in machine learning based classification, which is called as naive based algorithm. So naive based classifiers or naive based classification, it is a supervised machine learning algorithm that uses Bayes theorem to predict the class of a data point by assuming that all features are conditionally independent given the class. So we assume that features are all independent and for the given class, and we try to predict the class for the new features which we got at this moment. So that can be mathematically written as follows. So these are the features. So at this instant we got a set of new input or the new evidence, and we would like to find out which class it belongs to. And in order to find this, we apply the Bayes theorem. We assume that this is in the form of a posterior, and we would like to take the knowledge of priors, likelihood function and the evidence to compute this posterior probability. So let us see, if you take an example, this is how it looks like. So for a given set of words, we need to classify whether it is a spam or non-spam. And this type of inferencing is called as Bayesian inferencing. We are utilizing the Bayes theorem to make a inference about a certain input. So this is called as Bayesian inference. So this is how mathematically looks like. This is the posterior probability which we would like to find out, and these are the individual features, n features, which are conditionally independent for a given class. So this, using the Bayes theorem, this can be represented as probability of x1, x2 and so on xn for a given class into probability of class. So this is the prior information, and this is the likelihood function, and divided by probability of x1, x2 and so on xn, which is the evidence. So this is the evidence which we have observed now at this moment, and our goal is to find out what class it belongs to, assuming that these features are conditionally independent for a given class. And we know, so in order to find out this value and determine which class it belongs to, so we assign to that particular class whichever has the maximum probability. So these particular features can belong to various classes based on different levels of probability. So we would like to assign these features to one particular class whichever has the maximum probability. So in order to find it, we don't actually compute the exact value, we just want the top portion because the bottom is constant for all the classes. So this particular component is proportional to the top portion, and so we would like to find out this component, which is the likelihood function and the prior information. So in order to do that, we are applying the conditional independence assumption which we have made between the features. So so as it is shown here. So let us now apply this and see how we can do classification, and this is also called as maximum a posteriori classification, or map, shortly called as. So let's see more details about it. So this is what we have understood. So for a given set of features, we should find out what class it belongs to, and this is proportional to the prior information and the product of these likelihood conditional probabilities. So given for feature for a given class. So if we know these two information, we can compute this posterior probability. So let's see how we do that. So this is what is prediction we are going to do. So we would like to find out that class for which this particular overall posterior probability is maximum, and we assign this new feature set to that particular class. So whichever class has more probability, the particular feature set is being assigned or will be assigned to that particular class. So choose the class with highest probability. So let's see what all different types of naive Bayes we have. So before that, I would also like to clear that it is a supervised algorithm because we are having some prior information about it, and we are computing these probabilities based upon the prior information. So it is like a some sort of information which is available earlier, and later you are trying to find out for a new set of input. So it comes under the supervised machine learning algorithm. So these are the three types of naive Bayes we have. So we have Gaussian naive Bayes, and multinomial naive Bayes, and Bernoulli naive Bayes. The first difference between these three types is the feature type. The feature values are continuous in the case of Gaussian, whereas in naive Bayes we usually take the count data. So how many number of times a particular word has occurred, something like that, and this could be binary data, whether it is yes or no. So distribution is, this is Gaussian distribution, this follows a multinomial distribution, and this is a Bernoulli distribution. And an example, something like height, weight, these are all continuous values, whereas in multinomial naive Bayes we use word frequency, and in Bernoulli naive Bayes we use binary information about the word, whether it is present or not. So applications are there in medical diagnosis, sensor data for Gaussian naive Bayes, and news classification for the multinomial naive Bayes, and simple text classification for the Bernoulli naive Bayes. Let us discuss more details about Gaussian naive Bayes by using an example. Let us consider this data. We have 6 persons with their height, and we are classifying into 2 classes, fit or unfit, based on their height. So here the height is continuous, which means that it can take any value, any real value. So we would like to classify for any new unseen data into one of these categories based on this information. Let us consider a new height which is 178 centimeter, which we would like to classify into one of these classes as fit or unfit. So first we compute these two probabilities, probability of fit given height as 178, and also probability of unfit given height as 178. So whichever probability is more, we kind of classify this height data point to that particular class. So in order to find these probabilities, which are actually the posterior probabilities as per these naive Bayes. So in order to do that, we need to first get the priors, evidence, likelihood function, all those things. So first let's compute the priors for these. So as you can see here, we have in total 6 points. Out of that, there are 3 points belonging to fit, 4 and 3 points belonging to unfit. So the probabilities would be 3 by 6 and 3 by 6. So once we have found the prior probabilities, let's compute now the likelihood function and likelihood probabilities, and also the evidence probabilities. So likelihood probabilities we can know only when we know the Gaussian distribution. So we don't have any details regarding distribution, except that we have these few samples. So there are 2 classes, one is fit class and unfit class. Both we in Gaussian naive Bayes, we assume that both of them come from a Gaussian distribution. So in order to find out the parameters of the Gaussian distribution, we utilize the maximum likelihood estimates of those distribution. So we use the samples to compute the MLE estimates of mean and MLE estimate of variance, and thereby later we compute the likelihood probabilities. So in order to do that, so these are the 3 samples we have for the fit class and 3 samples for unfit class. So sample mean for this is given as follows. Which is taking out the average and dividing by n. So this is the maximum likelihood estimate of the mean for the Gaussian distribution, and this is the maximum likelihood estimate for the variance for the Gaussian distribution. But you have to note that this is a biased estimate. We also have one more thing, which is an unbiased estimate, where we divide by 1 by n minus 1. But when n is large, they become more or less same. In the main famous packages, Python packages like sklearn, they use 1 by n, but for large values of n, it does not matter. So, but basically we have these 2 estimates, and we are going to use this mean estimate and also the variance estimate to find out the Gaussian distribution and thereby compute the likelihood values. Let us compute the sample mean and sample variance for each class. So we have 3 points. So if you take the average of those 3 points, we get the sample mean. And if you take the variance, compute the variance of those 3 points with respect to the sample mean, we get the variance value. So we can do the same thing for unfit class. So once we know both these parameters, we almost know the distributions completely. So Gaussian distributions can be characterized by these 2 parameters. So once we know this, our goal is to find out for some unknown value, something like 178 centimeter, whether it belongs to class fit or class unfit. So let us see how we can find it. So let's compute the value of the probability for the data point height as 178. So when you compute this likelihood, so for fit class, x would be 178, and we have the parameters mu and sigma square. So the probability of 178 given fit, which is coming, this is a Gaussian distribution. So this likelihood probability is actually a Gaussian distribution, and we using the Gaussian tables, we can compute the value of these. So that would be 0.074. So in the same way, when we compute for the unfit class with a mean of 155 and variance as 16.67, so we get very low probability. So by this itself, we could say actually that this has more probability, but we know how to classify. So we compute the product of these priors and the likelihood function. So posterior probability, we get it. Posterior probabilities we compute based upon the priors, likelihood probabilities and the evidence, but we know that denominator is not needed, so we are just using the prior probabilities and the likelihood function. So when you multiply this, we get this is a probability 0.037, and when you multiply this, we get a very low value. So by just comparing this, although these 2 values are not actually the posterior probabilities because there is a evidence term which should be in the denominator, but since it is common for both these terms, for comparison, it is enough for us to find out just the numerator and find out which class it belongs to. So since this value is more, we say that 178 belongs to class So by graph also we can see here, it is lying here. So there is a certain non-zero probability for 178 for even the unfit class, but it is very low. It's just that the probability that 178 belonging to fit class is more as compared to unfit class. So this is how we try to compute the posterior scores and thereby determine which class it belongs to. So this is how Gaussian naive Bayes works, and so this is what we have done. And so let us now see the overall summary. If it is 178, it is falling somewhere here. What if the value is 165, which is exactly in between? So when it is exactly in between, or when the probabilities are same, we cannot conclude anything whether it belongs to unfit or fit class. So based upon at which point it falls under, we can determine which class the new data point belongs to. So this is how Gaussian naive Bayes, which is a supervised machine learning algorithm, utilizes the labels and the data points to compute the Prier's likelihood function and its estimates like sample mean and sample variance, and later during the classification or during the testing stage, we use the same probabilities to compute the posterior probability and determine which class it belongs to. So this is how Gaussian naive Bayes works. Gaussian naives. Here, instead of raw data, we have already computed Prier's and also the statistics. So there are three classes: apple, orange, and banana, and we are supposed to find the new fruit to which class it belongs to depending upon its parameters, weight and diameter. So our goal is to find out the which fruit it belongs to. Given the data what we have is the weight is 140 grams and diameter is 6 centimeter. So we know we need to find out the likelihood probabilities, and we also know that likelihood probabilities are Gaussian distributed with its appropriate mean and variance parameters. So we have been given each of the mean and variance parameters for each of this class. Now we need to find out to which class this is most probable. So in order to do that, so first we will be computing for each class the posterior probabilities, which is the multiplication of the Prior probabilities and the likelihood probabilities. We know that features are independent, so they have been written as product here. And so if you compute the score for apple, we will be having Prior probability of apple into probability of 140 weight given apple and probability of 6 diameter given apple. So when you compute these values, we get as follows: 0.00176, and these values we get it using the Gaussian tables. So we know that this is Gaussian distribution and its parameters, mean and variance, also we know it. So therefore, using the tables, we compute these values. In the same way, for orange we compute it, and also for banana we compute it. So out of these three, we can clearly see that apple is having the highest posterior score, and therefore we classify the new fruit belongs to the apple. So this is what the predicted class is apple. Important thing to note is we never computed the denominator, which is the evidence, because it is common across all the classes. So we are only finding the numerator. That's why we are calling it as posterior scores instead of posterior probabilities. So that's how we apply Gaussian naive Bayes in this case. So let's now go to multinomial naive Bayes, which is the second category of naive Bayes. And here, as we know, we use count as the feature. So for example, in a given sentence, we suppose if we want to find out whether a given mail is a spam or a promotion or a normal mail, you will be counting each of these words, how many times it has occurred, and we tabulated this here. For example, you have 6 emails, E1 to E6, and in each of these emails you have found out the occurrence of each word. We have counted the occurrence of each word and we have listed it here. So suppose if you assume that if we have such a data where we know the frequency of the occurrence of each word, and also we know the nature of that mail, whether it is a spam or promotion or a normal mail, given this data you can find out for a new mail which category it belongs to. You can classify the mail as a spam or a normal or a promotion. So once again, this is also a supervised learning. This is the known input data and its corresponding labels, which we are considering as an input, and later during the testing stage, for a new email we classify into one of these categories. So in order to do that, multinomial naive Bayes, also we compute the Priors. So this is how Priors will look like. So there are 6 emails. Out of that, there are 2 emails belonging to spam and and 2 belongs to promotion and 2 belongs to normal. So the priors are all equal here. And next is we count the words per class. So for example, spam mails, there are total of 8 words. In that 5 words have free, 3 words have win, and there are no word with meeting. So in this way we compute for promotion and also normal. So once we know the occurrences of each word in each category, we can apply the compute, we can do the Laplacian smooth. So this we do it to avoid unnecessary zeros, because when we multiply with zeros, it automatically nullifies everything. So to avoid it, we smoothen it, which we call it as Laplace smoothing. So what we need is we need the count of a particular word in a particular class. We add a +1 to avoid 0, and we divide it by total words in the class plus vocabulary size v. So this we compute for each of this class. So when you do it for free in this and for the class spam, we get something like this. So these are the conditional probabilities or the likelihood which we are trying to compute. So using this formula, we compute it. In this way, we have for win meeting in the spam category, free win meeting in the promotion category, and also in the normal category. So when you compute all this value, we are actually computing the likelihood function values. And this likelihood, we know the posteriors are a product of posterior scores are proportional to the likelihood values and also the priors. So we have computed the priors and we have also computed the likelihood values. Now let us see how we compute the posterior scores. So this is what I was saying. Posterior score is proportional to the prior and the product of the likelihood functions. So here we have to observe that xi is the number of times that word has appeared. So each time we are multiplying with its associated probability. So therefore we are having power of xi. So and we know v is the vocabulary size, and wi is the word in the vocabulary, and c is the class. So let's apply this and do the multinomial naive Bayes. So this works very much in text classification. So let's take this test sentence, which is test email, which contains 2 free words and 1 win word. So this is the word count for the given test email. So when you apply the posterior, when you want to compute the posterior scores, so we do for this particular word, which is wi, we compute the likelihood values. So given it is a spam, what is the probability that it is free? So in order to find out, we already have the posterior values for probability of free given spam. So we take that value and we substitute here and we compute these values. So in the same way, we can do for promotion score and also normal score, and later by using these 3 values, we can say whether that mail is a spam, promotion, or a normal. So as you can see here, 0.036 is more higher. So we can clearly say that the mail which is given with this content comes under the category of spam. Let us discuss about one example of naive Bayes. Here the data is assumed as categorical. So let us see first a general example, and later we will also see the specific examples related to Gaussian naive Bayes and multinomial naive Bayes and also Bernoulli naive Bayes. So here this is how the data looks like. We have a set of features: outlook, temperature, humidity, and windy, and this is the decision. So we play golf or not is decided upon this type of data. This is the existing training data we have, and we know the output. So we can consider this as the labels, and these are the features, and these features are categorical. So they are not continuous, they are not word counts, or they are not binary. So they are categorical. So it's somewhat slightly different to the ones which we have discussed, and our goal is to actually find out for a new data for something like this. So today is sunny, hot, normal and false, and we have to find out whether we classify these as yes or no for the question whether we play golf or not. So in order to find out, first we need to find out this posterior probability, which is probability of S given today, which is the product of likelihood probabilities and the probability of S, which is the prior probabilities, and this is the evidence. So as we know, we compute both the numerators and try to decide whether it is whether it comes under the category of playing golf, yes or no. So in order to do that, first let's compute this likelihood function, which is today contains 4 features, and we know that we assume that they are conditionally independent, so we can write it in the form of a product, and this is the prior probability. So let's compute each of these and thereby decide. So first one is the probability of yes. So there are among 14 data points, there are 9 data points which has output as yes, so the probability is 9 by 14, and probability of no is 5 by 14, and for each individual feature, sunny and hot, normal, false, we compute the probabilities in both the categories. So these are the likelihood probabilities, and so for example, for whenever the data input is yes, we try to see how many instances where we had sunny. So when it is yes, so we had in this case and this case second, and we also have third case sunny, and so there are 3 cases. So therefore the total 9 cases are there for yes, and out of these 3 cases we also have sunny, so the probability is 3 by 9. So in this way we compute for each of these features, and later we compute the overall likelihood probability of today given S as a product of individual conditional probabilities for both yes and no, and later we will see which of them and this 9 by 14 is actually the prior probabilities, which is probability of yes, and 5 by 14 is the prior probability, which is the probability of no. So once we get these posterior probabilities, posterior probabilities in this case, because we are using the k term also, which is the denominator, which is same for both the terms. So once we compute these posterior probabilities, whichever has the maximum probability, we assign this particular new data point to that particular class. So here yes has more probability, so for the given condition, today's condition, we indeed play the golf. So that's what the posterior probabilities are saying. So this is another general example of naive Bayes, where the input features are categorical. Let us see one example in Bernoulli naive Bayes. As we discussed earlier, Bernoulli naive Bayes contains features as binary, and it follows a Bernoulli distribution. So let's take this email classification example where the classes are spam and normal, and our vocabulary which contains 3 words: free, win and meeting. So this is the input raw data we have. There are 6 emails, and in each email whether there exists this word or not is represented using this number 1 and 0. So for each word we have listed whether it exists or not, and the appropriate class it belongs to has also been given. So since it's a supervised learning, we have both labels and the input data, and in the case of naive Bayes, we first need to compute the posterior probabilities in order to classify the new test data. So to compute the posterior probabilities, we need to know the priors and also the likelihood probabilities. So first we'll compute the priors. So priors can be, there are 6 emails here. Out of these, 3 are spam and 3 are normal. So the probability is 3 by 6, and for both the spam and normal. So now let's compute the likelihood probabilities or the conditional probabilities. So first we'll find out in how many emails it has been appearing, how many times it is being appeared. So this is for spam and this is for normal. We compute the conditional probabilities using the Laplace smoothing. The general Laplace smoothing equation is given as follows, where n indicates the total samples in that class, and k indicates the number of possible outcomes. In the case of binary outcomes, k value will be equal to 2. So for this particular example, we will have a formula something like this, where dogs, n is replaced by dogs, number of dogs related to that particular category. So if you do for the first example, so for the spam, we have 3 documents where which are related to spam, and the free word is appeared 2 times, so we replace count as 2 and n as 3, and we compute the value of the conditional probability. In the same way, we compute for win and also for meeting. So if you see the meeting did not occur any time, and total number of emails are 3. So in total, we get the probability as 0.2. So when you come to the normal, we don't have free or win in any of these emails, normal emails. So the output is 0. So we are adding this one just to make sure that we never have a 0 as a conditional probability. That's why the Laplace smoothing have this 1 in the numerator. And for win, we also compute in the same way, because there is no term called win in the email, test email. And also finally, the meeting has occurred 2 times, so it is 2, and there are 3 emails related to the normal, and therefore we computed the conditional probabilities as shown here. We go and compute the posterior probabilities as follows. So this is our new email, free and meeting. We have to classify whether it is a spam or normal. So free is occurring once, and win is occurring 0 times, meeting is occurring 1 time. So when you compute the posterior probability or the posterior score, which is the product of the prior and the likelihood probabilities, and we know that they are independent, so we have written it as a product. So we compute for each of these cases. So when we do it, we have probability of spam, which is this prior probability, and first one is probability of free given spam, and the second is x2. Here x2 indicates the win, and we know that in this particular test input it is 0. So we want actually the probability that it does not exist, so it is 1 minus of probability it exists. So that's how we are writing here, and the probability of meeting given spam. So meeting also exists in the test input. So we compute the spam score. This would be the spam score, and in the same way for normal score we compute it. So out of both, we can clearly see that it is normal is more. So we categorize the input test email as normal category. So this is how we use Bernoulli based naive based for classifying a given email into spam or normal category. So this is how these are the examples on naive based in all the 3 categories. Thank you.